we're picking up from where we left off with sets, okay? We're kind of doing this light introduction to set theory. And we covered union and intersection. We played around with, this using star args to perform operations on multiple lists that we're passing in. And we've been treating lists as if they're sets, but at the end of the day, there is a Python data type called a set, and that's what we're going to end up using to qualify some of these set operations later. Probably later in the lecture today, actually. So let's just pick up where we left off. The next thing we're going to consider is the difference of two sets. And set difference is very simple. Let's see how we can think about it. So we've got this, the classic drawing. We've got a sample space S, and we've got, we've got A, and we've got B. And the difference that I'm going to describe as A minus B, or A dot difference of B, it's a subtractive approach where any element that's in B that's in A, we're going to exclude, right? So we're going to include everything that's in A except for what's in B. And so here we're just taking, you can see we're just taking kind of a chunk out of A. What does that mean on the ground? Well, I'm going to leave that for you to interpret and have you write the difference function. So, well, you know what? Let me concretize this just a little bit. Let's say we have we have a set A, and A is composed of let's say a few items. Let's do 1, 2, 3, and 4, and B is composed of 3, 4, 5, and 6. Well, A minus B is going to yield this new set that's just the elements that are in A that are not in B. And similarly, B minus A will yield something, this is a simple expression. We're just going to get 5 and 6 out of this, right? Because 5 and 6 do not exist in A. 3 and 4 are getting, and 3 and 4 do exist in A, so we're going to remove them from B. So this is the idea of set difference in a more, kind of concrete way. And something to realize, we're not going to perform set difference on multiple sets, right? Set difference is a kind of a two-set operation. So why don't we, I'm going to have you write a function, there we go, that's better. So I'm going to give you 4 minutes to write the difference function, and think about what difference should take, right? It's going to have two parameters, one list and the next list. So you've got the list that you're subtracting from, and we're going to assume that's the first parameter, and the list that you're using those elements to subtract from the first list, right? That'll be the second parameter. So let's go ahead and put 4 minutes on the timer and go for it. Okay, so let's go ahead and code this. I think you'll see this is a pretty simple function, right? So I'm going to define difference, and we're going to pass in. I think I've been calling these list 1 and list 2, and so we're going to think of list 1 minus list 2 in this form, and we're going to get the set difference, which is going to be an empty list that we collect into. For each item in set 1, we can just check to see if that item is in set 2. And if it's not in set 2, if item not in set 2, sorry, I have these as a list, don't I? If item not in list 2, then the set difference is going to collect that, right? So append that item, and we can return the set difference. Okay, so let's look at, oh gosh, where are these? There we go. I'm just going to copy these down to here, and let's look at the difference between, well, let me resize this a little bit. Let's look at the difference A minus B. And it should be kind of obvious what this is going to give us, right? So we've got bat, cat, dog. Once we get to dog, weasel, dolphin, zebra, right? These are shared between the two, so we're going to exclude those in the result of this operation. So let's get the difference A minus B. Oh, set difference is not defined. That's because I misspelled it. Try that again. And we're just getting bat and cat. And that's what we expected, right? We expected to get these first two items that are not shared with B. Notice that this is a very different operation if we say B minus A, right? Sounds like somebody's mic is on, if you want to grab that. Okay, thanks. All right, so we're going to get a very different result, right? We're getting squirrel and vole, and we can see why by, we can just look at this. Squirrel and vole are not in A, but everything else is. So same idea as, but, the opposite operation. Okay, so there's one more operation that we're going to think about here. And this is going to come up quite a lot. It's the complement. So the complement, we're going to widely talk about the complement. And I'm going to explain this in two ways. I'm not only going to explain this as, the idea of the opposite of a set. I'm going to try to put it in terms of probability. I'm going to seed that idea, and we're going to see how often this comes up as we go forward. Okay, so we'll start with, again, our space S, and we're only going to think about the subset A. So if we're talking about the complement of A, which we represent in a number of different ways, I'm usually going to do this. I'm usually going to say not A, but another way that you might see this is A with an overbar. That means not A. Another way is like this. Tilde A means not A. Or like this, A prime, right, means not A. Or like this, not A. Why do we have so many of them? Because there are a lot of different fields that have, sets and logic in them. I'm going to try to be consistent about doing this, although I probably will do this sometimes. But I'm not going to worry about all the others, the tilde and the little corner bar, whatever, I can't remember what that's called. Okay, so when we're talking about the complement, what we're talking about is everything that is not A, right? And that's, I think, why the language not A is kind of nice here. So it's everything in the set, in the containing set, excluding the subset in reference, right? So anything that is not A is the complement. So think about what we need here if we're going to describe the complement. If we're going to write a function that's going to give us the complement of a set. Well, we need some things for that. And what we really need is we need to compose the containing set for this. And to do that, well, what's a way that we could do that? How, if we're thinking about sets A, B, and C as being exhaustive of the sample space, right, of the containing set, what would be a way that we could compose the sample space? Yeah, exactly. A union B union C, right? We can just union all these together. So we have that function, the union of multiple sets. And I'm sorry, let me I think I said this before, that I would share this whole thing. I would just copy and paste all of this in case any of you don't have it. And let me just do that really quick, since you'll have some function dependencies as we go. Sorry for that big wall of text, but you should have all of these functions now that are in this document. If you don't have them already, they're all there now. Okay, so in this case, we can just compose the sample space with the union of A, B, and C. Now, we could throw other things in here, right? We could say that, oh, maybe there's some other set like this where we've got, an eel. I did do animals. I was like, did I do sports and then put an eel in alongside basketball? But no. But you know what? Let's put a basketball in there anyway. It's some sort of basketball that's been granted life. All right, so we can go ahead and do that. And these are not contained in A, B, or C, right? Like the elements of D are not in A, B, or C. Now, when we write the difference has to be against the sample space, right? So, when you're coding this, you'll want to pass in, well, you could do this either way. You could pass in the sample space and, some list. And then you're getting the complement of the list against the sample space. All right, so let's do, I think this should be a pretty quick one. Maybe we can do 4 minutes. Yeah, let's do 4 minutes on it. And I'll grab that, put that there, and yeah, go for it. Okay, so I didn't give you this hint because I wanted to see if anybody would pick up on it. The difference, we can think about the difference as being, the complement. My bad. We can think about the complement as being a special case of the difference operation, where, if you think about it, what we're really saying is we've got this set sample space, right? And we're subtracting from the sample space the subset list. So that should work. We can return the difference of the sample space against the list. So let's call this and see what we get. So let's get the difference from A, or sorry, let's get the complement of A, given what we know as our sample space. And what we're getting here is squirrel, vole, manatee, sloth, eel, and basketball. And notice that nothing that we've returned here is in A, right? So anything that's been anything that's in A has been excluded. Now, this isn't the only way to write this, obviously. There's another solution that I saw. The other solution that's in the Slack is completely reasonable, right? Where we make a copy of the sample space and then we remove out of the sample space, whatever is in the list that we passed in. That's completely legitimate. I'm encouraging a little bit of function dependency as we go forward, right? So, can you utilize this function we wrote before in the current function we're looking at? Okay, so I think that might be it for our intro to set theory. Okay. There's actually a problem here that I think is it's a really good place to start thinking about probability. That said, I think I'm going to skip it, and maybe we can come back to it. I think maybe there's a breakout here. I'll show it to you. How about that? I'll show you the breakout, and what I'm going to say is that we'll probably move this to. We'll probably jump back to this breakout. Maybe after class, I'll just put it in the slides for probability, for basic probability. In this case, or in this challenge, we would write out the sample space for a random experiment that has 3 steps. And we haven't really talked about this. I think it's going to be more helpful to start thinking about counting, right? So we've built this idea around sets, and we're going to expand on that a little bit. And then we're kind of going to pivot and look at counting. And those may seem like 2 disparate things in a way, but they're actually 2 sides of the same vision of probability that we're building. So, we talked a little bit about random experiments. We can have an outcome, rolling a 4-sided die, then flipping a coin and flipping a coin a second time. Well, one of the outcomes could be 3 heads, tails, right? Another outcome could be 3 tails, heads. If we wanted to create a sample space, it would be the exhaustive set of outcomes. But we will come back to that, and we're going to not just come back to that, but we're going to focus on these kinds of phenomena quite a bit. So with that said, let's switch gears. And I'm going to move to a different file. So it's going to be, is it 03? I think it is. Yeah, and we're going to start off looking at axioms of probability. So if you're following along with the slides, I'm switching to the let's see. Let me tell you the file name. It's 19 _ axioms of probability .md, and I believe I'm linking to it in the original post for today's class. So what we're going to be talking about really is laws of Boolean logic, okay? And those same laws apply to the algebra of sets. I've got a big list of these, of the things we're going to cover, and we're not going to cover them with great depth. We're going to cover them with a little bit of depth, a couple of them with a little bit of depth, and the others we're going to kind of be a little hand-wavy about and just say, hey, this works this way. So this is our list of, this isn't completely exhaustive, but this is going to be our list of Boolean logic or logic laws or set algebra laws. We're going to think about, initially these three, we're just going to, posit that there is a commutative, associative, and distributive quality to certain set operations, right? Like union and intersection. We're also going to talk about taking a logical construct or taking a set operation and transforming it into another equivalent set operation, oftentimes a simpler set operation. And the one of these that's really, that you'll need to learn eventually is De Morgan's law. De Morgan's is going to come up. It's the kind of thing that if you go to a job interview, somebody will use that as the low bar that they make you get past. They give you a De Morgan's problem. And if you don't know De Morgan's, well, you might be, they might assume that you don't have the foundations for something else. You don't need to know, let me think about this. You don't need to know De Morgan's for the technical interview. There is kind of a lot of material regarding sets in the pre-course for the DSI. And you are expected to know De Morgan's and some simple set operations for the beginning of the DSI. So let's get into it. So as I've been saying, the set algebra laws can be equivalent, made equivalent, roughly equivalent to the Boolean operation laws, to Boolean logic. And in Python, we can see this pretty clearly, right? We can think of union as being like or, and we can think of intersection as being like and we can think of complement as being like not. Now, why can we do that? Let me get a little abstract here with how we might represent a set. So, So if we've got true, right? If we've got something as true, and we say true and false, well, we know that this operation is going to evaluate to false, right? For an and operation, both sides of the and need to be true. Now, why can we think of this as being similar to Boolean algebra? To set algebra. Well, what if true represents some quality of a set of items, right? Where true is, let's say this is 1, 3, 9, 7, 15. And we are going to, let's think about this this false as representing the set containing I don't know, 1, 4, 9, 12, 3. And there's some rule involved here. And the rule that that we may have defined is are all items odd? Well, in this first set, we can see that all the items are odd. Okay. In the second set, we can see that they're not all odd. We have 4 and we've got 12 in here. And that's where, let's say that's where this true is coming from, and that's where the false is coming from. And as a result, we can think of true as being representative of some set of events, right? And that gets a little bit maybe phenomenological, right? Where we're saying, okay, well, we've got this outcome, or we've got this set of outcomes. Are all the outcomes like this, right? Or does this set contain this kind of outcome? And the rule through which we define, where we define these arrows, that rule down here, that doesn't even need to be consistent, right? That only needs to apply to one set. We could actually, let's say this is the rule for this, and then the rule over here is going to be divisible by 3, right? Well, no, not all these values are divisible by 3, so we still get false. We can have these two separate rules. So this is kind of the representative equivalence in some way between set algebra and what we think of as Boolean algebra, right? Where a true can represent some rule on a set, and a false can represent some rule on a set not being satisfied. Now, one of the interesting things about this is, even though there's this kind of abstraction that we see, from the set to the Boolean that represents the rule on that set, the algebra that we use is consistent between sets and Booleans. So we can start thinking about union as or, intersection as and complement as not. Not exactly like that, but close enough. So let's... Oh, did I? I guess I didn't open the file that I meant to open. Oh, I see. All right, perfect. Okay, so let's think about this commutative property. And I'm going to demonstrate a couple of these, and the rest of them we're going to talk through, okay? So when we're saying something is commutative, what we mean really is that the operation can be interchangeable. The order of the operation can be interchangeable, just like in the algebra that we're familiar with. So the union of A with B is the same as the union of B with A. And that may seem obvious, right? Like, we're unioning this thing with this other thing. Well, it doesn't matter which one we do first. In the same way, the intersection, it doesn't matter if we intersect A with B or B with A. We're going to get the same outcome. And we can see this. I'm going to just write a simple... I'm actually going to use sets here in Python. So we have A, B, and C. And set 2 is going to contain C, D, and E. If we want to demonstrate this, that's easy to do, okay? So the truthiness of this can be demonstrated. I can take the union of set 1 with set 2, and this is how we would do that using set operations in Python, not the operations that we defined before, but if we have the data type set, there's a union method that we can pass in another set in order to get the union of the two. So is this going to be the same as set2.union of set1? And notice all I'm doing here is putting the equivalence operator in here, and we're going to get either a true or a false as a result of this. So is this going to be true? I think we know that it's going to be true, but just to verify, it is true. And in the same way, we could perform the intersection here, right? So the intersection, I can just swap out union for intersection, and that's going to evaluate to true as well. So that's our set logic. When we think about Boolean logic here, we can say A is true and B is false. So the way that we would perform this commutative verification is we would take A or B and just ask, well, is that the same as B or A? And I think this is something that y'all have played around with already, and you can see, well, yeah, that's going to be equivalent. That is these two statements, A or B and B or A, are going to be equivalent. And in the same way, see if I can, A and B is going to be equivalent to B and A. And so we should just see a bunch of trues, right? True, 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 true for all of these operations. All right, so the same is going to apply for associative. And this one, if you want to see, well, I'll show you the code for this. I'll just copy in some code just to show. So in associative, we're thinking about the groupings of these operations, right? So A union with B, the result of that then union with C is the same as A unioned with the result of unioning B and C, B or C, right? And all of this is going to be the same as what we're seeing here, right? And more often than not, this is what we would write. We wouldn't actually put parentheses around these. We wouldn't need to group these because it doesn't matter what their groupings are. And the same goes for intersection, right? Notice that when we write intersect, we don't put an operator in there. We just put the intersection of sets right next to each other. Kind of, we get that feeling of multiplication from it. And I think we see that here. So let's look at what this would look like in code. And I'll just copy some code in. So let's think of associative. So to get the idea of this, notice that first we're getting the, we're unioning set 1 with set 2. And then we're unioning in set 3 to the result of that. I don't think we have a set 3 up here. Let me just paste in a set 3. And this just sort of hammers home the idea that it doesn't matter the order in which you perform your unions or the order you perform your intersections. So I'm going to comment that out, and let's think about something that isn't quite as intuitive, and that's the distributive property. And I might actually draw this out a little bit. So if we intersect B with C, and then we union A to that, that's going to be the equivalent operation to unioning A with B and intersecting that with the union of A with C, okay? And we can show something approximate to that with unioning first and then intersecting with the union. So this is maybe I'm going to give you a little glimpse into doing this by hand, because I think that can be helpful. It's something that you're going to need to learn later, but I just want to give you a peek into this. So if we're talking A union with B intersects C, all right, let's kind of write this out. So let's say A is true, and let's say B is false. And let's put these, let's write out this A union B C, right? So this is A union with B intersects C. And we're describing this as being equivalent to the union of A with B intersected with the union of A with C, okay? So I'm going to show false as just being a big F and true as being a big true. And I'm going to start filling these in. Okay, so here we've got B B is false, false intersect true, right? And we're going to union that with true. And false intersect true is going to give us false, right? This is the same thing as and for us. And, and maybe it would even be more appropriate for me to do ors and ands, right? So or, and. So now we've got true or false. And true or false, well, only one of those needs to be true, right? So we get true. All right, so this is our ultimate answer on one side. And let's find out if this is going to be the equivalent of what we're seeing on the other side. So for union, we're going to think of that as an or, right? So A is true, B is false, and we're going to say and A is true, or I need a C in here too. Oh my gosh, y'all. Let me back up. B, C. I guess C would have to be true because I already composed it that way. All right. So true or true. Okay. Let me just make sure I'm not... Okay, awesome. All right. True or true is going to be true, obviously. And we're going to and that with true or false, which is true. True and true is true. So we can see that these two constructs are equivalent. Does that make sense? We could write code for this to verify it, but I think breaking these down in this way can be pretty helpful. So we just did that for B intersects C union with A. Let's do A intersected with the union of B with C. All right, so let's say A, I think we'll keep that as true, B will keep that as false, and C will keep that as true. All right, so we're saying A intersected with the union of B with C. And we're going to verify that this is equivalent to A intersect B unioned with A intersect C. And again, I'm going to take a little bit of liberty here and change our unions to ors and our intersections to ands. So this is going to be it's going to be true, that is, true and B, which is false, or C, which is true. And we can say false or true. Well, that's easy. That's true. True and true is going to be true. All right. A and B, right? So that's true and false. Or A and C, A and C, which is true and true. So true and false is false. Or true and true, which is true. Well, false or true evaluates to true, and we can see that those are equivalent. Okay. So let's kind of skim through some of the other laws. I think there's a lot that we could cover in this, but I mainly want to show you that there are simplifications of logic that we can perform. And this may not have a lot of gravity for you right now, but once you get into SQL, if you haven't looked into SQL much, this starts becoming important, right? It starts becoming important in designing networks as well. So networks in the sense of a neural net is a network, right? There are various kinds of neural nets that you're going to get into. And the way that we think about logic is going to affect how you operate in those spaces. Okay, so we have a couple laws that are called idempotent laws. And I think these are pretty intuitive. If you union an item with itself, if you say true or true, it's going to be true. If you say true and true, it's going to be true. Okay. I think that's pretty obvious, right? If you union a set with itself, well, you're just going to get the same stuff. If you intersect a set with itself, well, you're just going to get the same stuff. So I'm not going to draw that one out, but it is important to point that out. There are a couple almost tautologies. They kind of go without saying. If you intersect, if we have a set A and we intersect that with the universe, with our sample space, well, the intersection of that is just going to be A, right? So, we have the letters A, B, and C, and those are in set A. And then we have the entire alphabet, which is the sample space. Well, we intersect A with the entire sample space, with the entire alphabet, and we're just going to get A, B, C, right? So we would get that intersection of itself. If we intersect, I said this yesterday, if we intersect something with null, with nothing, with an empty set, we're going to get the empty set. And I think this is where things get a little more interesting in terms of, what I'm going to think of as, reductive logic. So we have this idea of absorbing. And if you're ever simplifying logic, absorption laws are going to come in and aid you greatly. You're going to take a more complex logical statement or Boolean, set algebra statement and end up with something simpler. So let's demonstrate this. We've got A, let's say A is true, and we'll make B false again. And we're saying that A union intersection A, B, and we're going to assume that that's equal to A. So we know over here that A is true. So let's write this out. Let's say A, let's say true, that is, or true and false. True and false, that is going to be false. And true or false is going to evaluate to true. And we can see that we can indeed absorb from this operation, we can absorb to just A, right? We've eliminated B from this. In the same way, and I'll keep the same values there. So A union, A intersected with A union B. And, again, A is true, B is false. We're going to assume that this is going to reduce out to A, okay? So we're saying true and then we've got this OR operation, right, where we're saying true or false. True or false is true. True and true is true. And we can see that that is indeed A. Okay. Got a few more of these. There's a couple that, again, are tautologies. And I think they just go without saying. The union of A with nothing is just A, right? That's what we call the identity property. And these are kind of cool, and, they're kind of big laws that don't really matter in your everyday operations. But complement laws for universal and empty set. If, not nothing is everything. Not everything is nothing. So that, again, is kind of goes without saying. I think this one does as well. The Involution Law. Just the idea of a double negative is a positive, right? So not A is just A. A lot of these I think are pretty obvious. And then there's some that are a little weird. And some of you who have, set algebra backgrounds, if you know the name of this law, when I was doing circuit design, I would use this all the time, this construct. And I never knew a name for it. But, let's walk through it and just verify that it's doing what we think it's doing. So let's say A is true again, and B is false. And we can say we're looking at A intersect B unioned with A not B, and I'm going to do this over bar for not, is just A. So this is A intersected with not B. That's what we're seeing there. So how do we think about this? How do we write this out? Well, this is just true and false, or true and not false. So let's solve either side of these. True and false, well, that's false. Or, well, not false is just true, right? True and true, which is true. We get false or true, that's true. And A, as we saw above, A is true. This construct, again, it's one of those things, you don't need to know it now, but you will need to know it later. And one of the things you can do, you can kind of start with a simple logical idea like true, right? You can simply start with true. And you can, think about true as being, well, that's true and true. Well, true and true is also, we can take that a little bit further and we can say, well, that's true and true or false, right? We can take that, we can continue down this path, and we can make more, you can take this in the other direction, right? You can start with a very simple logical outcome, and you can make a very complex logical statement. And after constructing that complex logical statement, you can then turn it back around and reduce it down to its kind of prime form. And when you use variables to represent, let's say A represents true and B represents false, you can start doing the same thing. You can interpose A and B throughout this, and we could throw a C in there too. You can compose complex logical operations, and you can then take A and think about it as a set, right? You can think about A as the set of items, like we could say A, B, C, and verify that these things hold true. And you can even do this with Python fairly easily using set operations. Okay, so let's look at just a couple more. Oops. And these are the main ones that you're going to want to take away. And I'll just verify these. Yeah, I'm sorry these use the tilde. I actually really don't like the tilde. I feel like I should replace tilde with an overbar. But that just means not, right? So I'm going to rewrite these. The first De Morgan's law is just, we've got A union B. And this is, there's an overbar that's saying not for that whole operation. So not A union B. And this is the same as not A intersected with not B. Now, notice that this is not a contiguous overbar, right? This is not A intersect not B, okay? So we can again do this, A is true, B is false, and start filling this in. So how am I going to write this in Python or as a sort of Pythonic-ish logical statement? Let's say this is not A, which is true, or B, and this other one is just not true, and I don't need these, but I'm going to go ahead and put parentheses around this, and not false. So let's go ahead and work that out. Just erase that. So true or B, true or false, that is. True or false is just going to evaluate to true. And then we've got not true, which is false. The equivalence here, so not true is false, right? Not false is true. False and true is false. And we can see that this is indeed true, or this is indeed equivalent, both these sides. Now the other one here is we've got A intersect B, and that we're going to not that operation. And we're positing that this is equivalent to not A unioned with not B. So again, A is true, B is false. So not true and false, true and false. And we're saying that this is equivalent to not true or not false. Keep making myself run out of room. All right, so true and false, well, that's false. Not false is true. Not true is false or not false is true, well, that's true. And we can see that that holds. At the end of class, if anyone's interested, I might draw out a quick circuit diagram. I think those can be interesting. They're kind of fun. And they give another perspective on these kinds of axioms. The main one that you want to try to commit to memory is this De Morgan's law, or these two De Morgan's laws. I think they come up more than anything else does, and in terms of your axioms of probability, logic, those are ones that you should be able to, I don't know, pull out of your memory when you get into the practice of data science. Okay. Yeah, I have a few slides here on logic gates, but we're not going to do that. I might stay on for, just show a quick one at the end of class for like 10 minutes because it's fun, but it's also not entirely necessary. Yeah, I'll leave it at that. Okay, so let's take 6 minutes, and when we get back, we'll get into actually, thinking about, we'll actually start thinking about how to approach probability. Okay. Yeah. And I'll answer that question when we get back as well. So I'll see you back here in 6 minutes. Okay, so let's start getting into, let's start getting into probability. Oh, I don't actually want, oh yeah, I do want to terminate that. One sec, let me just close that out. Okay. So the way that we're going to begin thinking about probability is through the lens of sets, and then we're going to consider probability through the lens of counting. And these may seem like, you know, two different takes on the idea, but they're not really. They're really the same thing when we get down to it. So there's this idea called cardinality, and I may have mentioned this in passing. Let's say we have a set S, and that's our sample space, and let's use the alphabet here. So A, B, C, oh my gosh, comma C, D, all the way to Z. And we have a subset A, which is just, you know, A, B, C, and let's say D. The cardinality, what is the, how many items are in S here, right? The cardinality is the count of the items in S. How many items are in A? When we talk about cardinality, we do this. We draw the same pipes on either side that we use to describe magnitude. Okay, so this is kind of the magnitude of S, and this is the magnitude of A. And probability, the probability of event A occurring, which is going to be the outcome, the letter A, B, C, or D, is going to be the magnitude of A over the magnitude of S. What is that? Okay, 15.38, so 0.1538. Now, you think about it, that's kind of it's a simple idea, right? Let's put it in some other terms. Let's do the classic of, well, we've got a bag of marbles, right? We always have these bags of marbles, and so here's our bag, and we've got, let's do red. We've got 40 red marbles. Oof. Sorry, apparently I can't write today. 40 red marbles, and let's have some green marbles. Got 20 green marbles. And let's say we have another 40 blue marbles. Well, close your eyes, reach in the bag. What is the probability of grabbing a red marble? So the way we think about this is it's the the count of those red items. Let's say in this case, that's going to be 40 over the total, 40 over 100. And we can see that there's a 0.4 probability or 40% chance we're going to pull a red marble. Now, this is coming from a kind of set perspective, and we're also going to find it necessary to build sample spaces pretty often, and I think we're going to get into that today. Let me just grab the other file that we're working with. Oh, you know what? I'll do this. Okay. So let's think of something fairly simple. Okay. Let's think of rolling 2 dice. And if we're going to roll 2 dice, what are all the possible outcomes of that, right? So this is a fair 6-sided die, and so a roll is going to be 1, 2, 3, 4, 5, or 6. And these are with equal probability. So what are all the rolls that we can make? Well, we can do 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. We can do 2, 1, 2, 2, 2, 6, and so on, where eventually we're going to have 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. We can put a rule on this, right? We can ask the question, we can ask a different kind of question than, what is the probability that you're going to get 2 and then 5 in your roll, right? Let's say we roll once and then we roll again. We could change this, change the rule on this, and we could say, well, what is the probability that the sum of your 2 rolls is going to be 7, right? So the probability of having an outcome of 7. Well, we would need to go through this and find all the outcomes that are 7, right? 1 plus 6 is 7. 2 plus 5 is 7. We've got 3 plus 4, right, is 7. We've got 4 and 3, and we've got 5 and 2, and 6 and 1. We can take that subset and we can divide it by the total number of rolls in our sample space. And that's going to give us the probability of 2 rolls summing to 7. So let's think about, I think I've got a breakout here. Let me... Before we get to the breakout, let's do this. Let's talk about the symbols that we use here. So I've been kind of tacitly, casually doing this. The probability of some event, right? P, that's what I do. I do P of that. Other people will do this. The probability of something. So the probability of A. Either of these is fine, right? That's the meaning is just what is the probability of this. Now, when we're writing this out, most of the time, if we want to look for the complement of something, the probability of not A, for instance, I'm going to usually write not, okay? And, that's the way we would ask that question. The probability of A not occurring. Everything but A. When we're talking about intersection, the probability of A intersect B, as we've been seeing it, we just put them right next to each other. Or we do, A intersect B. Like so. If we're talking union, it's just, as we've been seeing it, A union B. When we're talking about the probability of one event occurring given that another event occurs. That's something we haven't seen yet. We use this midline, this bar, right? Probability of A given B. We're going to have a whole lecture where we're dealing with that. So let's broach the idea of counting now. We're going to do a lot of counting in this class, and it may not be the kind of counting that you have seen before. And I'm going to try to make this, I'm going to try to broaden your idea of what counting is, okay? That's one of my goals in this class, is to take counting and make it a sort of foundational idea. So to do that, I'm going to define a sample space. I'm going to call it S, and it's just going to be a list for our purposes. And I'm going to put a cat, a dog, a ferret, and a goldfish in that sample space. So what is the cardinality of S? Well, it's 4 items. There's only 4 items in S. The cardinality here, we can also think of that as the base of a number system, of a counting system. And we can, let's say we have a room that has infinite cats, infinite dogs, infinite ferrets, and infinite goldfish. And we're going to reach in there and grab one of these creatures randomly, completely randomly. And then we're going to grab another one. We're going to grab 4 of them total. We could get 4 cats. We could get 4 ferrets. We could get a cat, a dog, a ferret, and another ferret, right? Like this is how we might think about this. So how would we consider all the possibilities here? We would count. We would start off by counting. So what do we have? We have a cat, a dog, a ferret, and a goldfish. Okay. We have a room with infinite number counts of each, and we're going to reach in and select 4. Let's reach in and select 3, just for convenience. So we're going to reach in and select 3 of them. How do we make an exhaustive set of possibilities for selecting 3? Well, turns out we're going to count. And I'm going to count starting at goldfish, 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 ferret, goldfish, goldfish, dog, goldfish, goldfish, cat. Okay? And then I'm going to go, okay, well, once we get to cat, we're going to turn cat back over to goldfish. And then we need to turn this goldfish over to ferret. So we get goldfish, ferret, goldfish, goldfish, ferret, ferret, goldfish, ferret, dog, goldfish, ferret, cat. Okay. So this is a way that we can turn these elements into a numeric system. And in lieu of writing all of these out, because it's going to take way too long and it's tedious and I'm going to get something wrong, I'm going to use Python to do this, and that's going to be very easy. But notice what we eventually end up with here is cat, cat, goldfish, cat, cat, ferret, cat, cat, dog, cat, 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 right? With everything in between. Does anybody have an idea of how many different possibilities there are here? What is the cardinality of our sample space? The way to think about this, we've got 4 elements, right? And exactly what people are putting in the Slack. Yeah. We've got 4 elements, and we've got 3 places. So this is just 4 times 4 times 4, or 64. Okay. So let's approach this with Python. I'm going to do this in a very, I don't want to say boneheaded here. I'm going to make an exhaustive set of possibilities for, drawing 3 pets. And notice I'm saying with replacement, okay? What I mean by with replacement here, this is why I'm saying there's infinite number of these. We could also think about it as you reach into the room, you only have one of each, you reach into the room and you pull one out at random, and then you put it back, and then you reach in and you pull another one out and you put it back. Either way works, right? That's why we say with replacement. If you pull it out and put it back, that's with replacement. You're replacing the animal. Okay, so I'm going to call this pet outcomes, and I'm going to use a for loop to count. I'm going to say for pet 1 in pets, for pet 2 in pets, for pet 3 in pets, and the way that I can construct all these outcomes is pet outcomes dot append, and I'm just going to do this as a list. Pet 1, pet 2, pet 3. And then I'm going to print this out. So for pet outcome in pet outcomes, let's print each one of those pet outcomes and see what we get. Name pets is not defined because I called it S. Let's call it pets. All right, so here, notice we've counted in pets. We have turned these items into a counting system. It turns out this is a base 4 counting system because we've got 4 unique elements. And we're making an exhaustive list, so this we could consider to be base 4. We're used to base 10, right? Base 10 is something we're all very familiar with. We all know how to basically count in base 10. That's very straightforward for us. When we think about this, so we go 0, 1, 2, 9, and then we roll 9 over to 0, and we increment the next place by 1. Well, if we're counting in base 4, we can go 0, 1, 2, 3, okay? We roll the 3 over to 0 again, and we increment the next place by 1. And, we can continue doing that. What's going to become very helpful is actually base 2, where we've got 0, 1, and then when we get to 1, we just roll that over, and then we get 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and we can keep going with that. Although in most cases we would actually prepend this. And so this is a base 2 system. This is what we might call 3-bit binary. That's going to come in really handy. We're going to revisit that multiple times. Okay, so now that we've got these pet outcomes, we can ask some kind of question of this, okay? We can, let's turn this into 4 pets really quick to accommodate the next slide. And so I'm just going to add another pet in here, so pet 4 in pets. And I will share this, and you're going to do something with this. So the question, given this idea that there's the cardinality of the subset over the divided by the cardinality of the sample space, let's have you answer this question. What is the probability that a person will select 2 or more cats when randomly choosing 4 pets? So I'm going to put 4 minutes on the timer, and I'm going to fix that typo. And you're going to have to write some code to solve this, okay? Do your best on it, and then I'll show you how to do this. We're going to be doing this kind of problem quite a bit. Okay. Do y'all want 2 more minutes on this? I know this is kind of the first time I'm throwing this type of problem at you. If you want 2 more minutes on it, awesome. I can also solve it because we're going to be looking at more and more problems like this. Give me a thumbs up if you want a little more time. Okay, I'm gonna start solving this. Oh, never mind. Let's give 2 more minutes on this, and then we'll come back and solve it. Okay, so let's go ahead and think about this. We are building a subset, right? We've got pet outcomes, and we're looking for what we're going to eventually need is, the length of some subset, two or more cats. And that's going to be divided by the length of our pet outcomes that we made. So pet outcomes. That's eventually what we're going to need. And that's kind of the magnitude or cardinality of the subset divided by the cardinality of the containing set. Okay, how do we do this? Well, we can just traverse the pet outcomes. So for each pet outcome in pet outcomes, we can append to this we can say if the pet outcome, the count of the occurrence of cat, see, did I call it? Yep, cat. If that's greater than or equal to 2, then we can append that to this 2 or more cats, right? Which I need to declare above. So 2 or more cats, make that an empty list, and we can append that, the pet outcome to that. And why don't we do 2 things? Why don't we traverse 2 or more cats here? Oops. So for item in 2 or more cats, let's print each item and take a look at this to see that we are actually capturing all of these. So it looks like the probability works out to 0.262, roughly 0.262. That's what I see some consensus with the results other people are getting. And we can see that in our subset here, cat, 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 dog, all of these have at least 2 cats in them, right? Cat, cat. There's actually an interesting pattern here, and I think this happens when you count. When you count and you build a subset through an end-to-end traversal, starting at the earliest item, which is going to be all cats, to the last item, you start seeing interesting patterns. And we're going to, when we talk about heaps algorithm, or when we talk permutations and combinations, we're going to see that a little bit more. The emergence of patterns when we do this sort of traversal, and how that can lead us to thinking algorithmically about solving a problem. At any rate, though, we've determined here that the cardinality of the subset of items where there are 2 or more cats divided by the cardinality of all 4 pet combinations, or 4 pet counts, instances, leads us to concluding that the probability of choosing 2 cats at least out of 4 pets is going to be around 26%. Okay, so let's look at another one kind of along these lines, very much along these lines. We're going to think about coin flips. And with this one, you're not actually building the sample space yet, okay? What you're going to write... oh, interesting. Okay, yeah. What you're going to write is a function called series of flips. And you're going to need this little bit. Sure, I can paste the solution as well. I just pasted in the function that you're going to use here. So you're going to utilize this function, and you're going to write another function called series of flips. There's going to be one parameter you define, n, and that's going to be the number of coin flips. And you're going to return a list of length n containing n random coin flips. So that's going to be... You can go ahead and start working on that. I'll snag this code. And this is the solution to the prior one that I'm pasting in. And I'll go ahead and set a timer. So this is what you're working on. You're going to need to use this function I'm providing that gives you the result of a coin flip. Okay, I'm going to go ahead and solve this. So let's see, I need to paste in the actual coin flip code. All right, so from random import choice, this is going to return either heads or tails with randomly one or the other. Okay, so we're writing this function, series of flips. And we're going to have n flips, whatever that is, right? 4 coin flips, 5 coin flips, whatever it's going to be. And I'm going to collect those like so. And I'm going to say for whatever in range n. When I say whatever here, it means that we don't actually care about this index value. So I put an underscore there, just saying we're not going to use it. We don't care about it. And for every one of those, I'm going to say flips.append, and I'm going to append a coin flip. At that point, I can return flips. And we should see, when I call this, we should see a series of flips, right? Let's do 12. And that's what we're seeing. So heads, tails, heads, 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 tails, tails, heads, tails, heads, heads, heads. Okay. So let me go ahead and throw that in the Slack. I think we have just enough time to try to tackle something that utilizes this function. All right, so let's think about, oh, you know what? I'm going to pull up this next breakout and code through it really quick. This is something we've already seen, but notice here we're doing a random draw, right? We're randomly getting these coin flips, for as many as we want, and there's an advantage here, and that advantage may not be immediately apparent, but we can put any, we can put a very large value of n in here, okay? We can do 10,000 coin flips. In fact, why don't I do that? It's going to be just to show you that that's something that is not out of the realm of possibility. Look how fast I just got 10,000 coin flips, right? Just like that. They're random, right? But what if I wanted to build the sample space of 10,000 coin flips? That's not going to be quite so nice. That could look like 10,000 nested for loops, and I don't think we're about to do that. I'm not going to do that on this computer and let it run for the next, I don't know, chunk of time. I'm not actually sure how long that would take. But what we can think about with this is that if we randomly sample, if we use some kind of random process, we can construct outcomes. I could do something like this. Well, let's count the number of heads that occur in 10,000 flips, right? And 5,033, 4,950, 5,067. You might notice that we're, jumping just above and below 5,000, which is kind of what we would expect. Given 10,000 flips and a fair coin, that's probably what's going to happen. We're going to be aiming right for the middle of that, a 50-50 chance, as it turns out. We can use sampling in that sense. We can use sampling to approach probabilities that we might have a hard time approaching through an exhaustive counting approach. And we're going to see that. We're going to see that in a number of cases coming up. So I'm going to solve this. Write a function called forFlip sample space, right? Def forFlip sample space. And it's not going to take any arguments. All I'm going to do is return all the possibilities in 4 coin flips. So, you know, let's say there are flips, heads, or tails. For flip 1, in flips, and I'm just going to do that 4 times in nested loops, 3 and 4, and I can say, let's just do, I'll make a collector here called outcomes, and I'll say outcomes.append, and I'm going to append a list that's flip 1, flip 2, flip 3, and flip 4. And then we can just return those outcomes. And if I run this, I'm just gonna say for outcome in, well, let's do this. Call this 4 flips, and I will just call 4 flip sample space. And I'll say for flip in 4 flips, or for, let's say, outcome in 4 flips. Let's just print the outcome. And you might have some intuition on what we're going to get here. We start with all heads, and then we, you know, heads, 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 tails, heads, heads, tails, heads, 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 tails, tails. We're actually just counting in binary, except we've replaced the 1 and 0 with heads and tails, or actually 0 and 1 with heads and tails. I'm going to just turn those around really quick, because often we might think of heads as being successful, right, and tails as being a fail of some sort, or heads as being, you know, or 1 as being true and 0 as being false, 1 being a success, 0 being a failure. And so I might think about this in terms of binary as tails, 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 or 0, 0, 0, 0, right? So this is counting in 4-bit binary, but we've replaced the 1 and 0 symbol with heads and tails. So we can take that a little bit further, and we can ask a question such as, what is the probability in 4 coin flips? You get exactly 3 heads. That doesn't mean 3 heads in a row, right? It means 3 heads. So how about that as a question? We can answer this given what we have here, right? We've got this outcome of 4 flips. So what we can do is we can say, let's call this 3 heads, and we'll just have that as a collector. And I'll say for outcome in 4 flips, if outcome.count of outcome.count of heads, right? Exactly 3 heads. If that is 3, then we can say 3 heads dot append the outcome. And if we want to know the probability that you get exactly 3 heads in 4 coin flips, well, we can just print the length of 3 heads and divide that by the length of 4 flips. And it looks like that is 0.25. So, you know, we're not necessarily seeing here how, let's say, how the sausage is made, right? What we are seeing here is how the sausage is made. And what we're sort of not looking at is the mathematical abstraction that we can get to from this. So, you know, when we're thinking about the probability in 4 coin flips getting 3 heads, well, what if we asked a different question? And I want this, I'm going to leave this as food for thought. What is the probability that in 12 coin flips you get exactly 3 heads? Well, you could do, you know, 12 nested loops, and we could answer that question. And that's not the worst approach or anything. I think that's fine. But we actually have other ways of solving this kind of problem. And I want to just mention the crux of this problem, right? If we're saying 12 coin flips, you can have 1, 2, 3, 4, 5, 6, 7. Oh, let me make that caps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'll replace 3 of those with heads. That's one possibility, right? And here's another possibility. And here's another possibility. And you can see that we can make different arrangements of this. We can make a bunch of different arrangements that will lead us to having 3 heads in total, right? We can ask other kinds of questions. What's the probability that in 12 coin flips you get 3 heads in a row, right? That's kind of easier to think about, isn't it? We can take these 3 heads and we can shift them to the left one at a time. We can count how many times that happens, and then we can simply take 2, raise it to the 12th power. That's the magnitude of our sample space. And, what would that be? That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that would be 10 over 2 to the 12th. So we can think about that in this, cardinality of A over cardinality of S format. We can also think about it in terms of counting. So that's food for thought for tomorrow, where we're really going to be digging into counting. Tomorrow's lecture is on counting. Okay, thanks so much. That's the lecture for tonight. If you have questions, stay on. I'm going to go ahead and stop recording.